the main topic of this first month of lecture, which is random walk in random environment. Okay, and for the moment, I will focus on the one-dimensional version of the model. And just to introduce the model, and I think it's a bit better to first tell you very rapidly what's a Markov chain. Okay, so what's a Markov chain? So the reason why I'm introducing this notion is because random walk in a random environment is a particular case of Markov chain. So we let E be a countable space. Okay, so when I say countable, I mean countable or finite. And the first definition is we say that Q from is a stochastic matrix on E if, okay, so, okay, by definition, it's an infinite real-valued matrix, okay? And we want it to satisfy two properties. So the first one will be that, well, for all xy in E, qxy is non-negative. And the other is that if you take the, okay, I don't remember which ones are lines or columns, but I think if you take the lines, yes. If you take the lines of the matrix, they define probability on E. Okay, so that's one definition. And the other definition is the one of Markov chain. So we say that Xn, okay, so that and E valued random process Xn is a Markov chain. With transition matrix Q if, okay, the probability that n plus 1 equal y, knowing that x0 is equal to x0, x1 is equal to x1, and xn is equal to xn. So if you know all the trajectory of the past, this thing is simply qxn. Y. And whenever, well, okay, for every n x1, xn whenever this makes sense. So whenever you can make sense of the conditional probability. Okay, so what this relation means, okay, is that the conditional distribution of xn plus 1 given xn x0 is given by q xn dot. Okay? Basically, if you know everything about the past and you want to sample xn plus 1, well, you sample according to this, which is a random probability, which only depends on xn. Okay, so what being a Markov chain means, okay, is that what happens at step n plus 1, depending on the whole past, is in fact only depending on your state at step xn. Okay? So this is the first observation. Well, a second observation is that this relation somehow fully determines the distribution of the process. So from start, we deduce that if you want to look at the probability that x0 is equal to x0, xn equal to xn, well, this thing, you can find that this is equal to this times q x0 x1, q x1 x2, q xn minus 1 xn. Okay? How do you obtain this? Well, basically, well, what you're doing is you're using star to first extract this thing, okay? And then you use it repeatedly, and either you stop whenever you find that this is equal to 0, or you continue up to the bit. Okay, so, basically, you know that these events, okay, well, of course, by union, they generate all cylinder events, so they fully determine the distribution of the process. Okay, so the conclusion of that is that given a probability on E, probability nu on E, and a stochastic matrix Q, E times E, there exists a unique Markov chain xn n on e to the power z plus with x0 and transition. Matrix. What does unique mean here? I mean that, well, I mean that there is a unique distribution on this space, okay, under which the process is a Markov process with initial condition nu and transition matrix U. Okay. Yeah. Somehow, what this show here is uniqueness. Well, for existence, you have to do the usual Kara-Theodori stuff. It's really not the topic of this course. Okay, so now let's define the random walk in a random environment. And what I'm going to do is I'm going to say that it's a Markov chain, and I'm going to specify its transition matrix. So far, so good. Any question? So given a sequence omega x indexed by z, we set q omega xy to be equal to, well, omega x if y is equal to x plus 1, 1 minus omega x if y is equal to x minus 1, and 0 if y, well, is not either of these two values. Okay, and well, you can check that q omega defines a stochastic matrix on z times. Okay? Because these two things sum to 1. Okay, and definition. The random walk in random in environment omega, this thing is omega, is the Markov chain with transition matrix q omega. Okay, so I'm not specifying the initial condition, and Well, the reason is that we're really focusing on properties that really do not depend on the starting point. Okay, so yeah, let me introduce some notation. So we let P x omega denote the distribution of the random walk in environment omega with initial condition x0 equal x. Okay, we are going to focus on cases where the initial distributions are initial distribution. Whereas the initial distributions are Dirac masses, well, simply because the other cases you can obtain them by convex combinations. So. Okay, and usually we are going to drop the index x if x is the origin. Okay, just a convention. Okay, so this really corresponds to the picture I drew last time. Okay, you are on the axis z. Okay. Well, let's say that 0 is here. Let's say that xn is equal to y. Okay, then at the next step, you're going to jump independently of your past to y plus 1 with probability omega y and y minus 1 with probability 1 minus omega y. Okay, so now what's a random walk in a random environment? Well, we are going to be particularly interested in the case where omega x are IID. Okay, so I'm going to use P is the probability associated with omega. Okay, and we are going to assume most of the time that omega cannot be close to 1 or close to 0. Okay, and this is an assumption which is called uniform ellipticity. Most of the time you won't use it fully, but you will see that it will give us some properties for free, and these properties are useful. And it's not well, okay, it does not induce a lot of lack of generality. Basically, everything you do under this assumption, you can do it under optimal assumption with some work and sweat. So yeah, I think this is a good choice. Okay, and there are basically two ways to look at the random walk in random environment. So the first thing you can do is fix the realization of omega and look at this measure. Okay, so first point of view. The quenched random walk in a random environment. So you sample omega according to P, okay, and then study P x omega, okay. And basically the kind of statement you're looking at when you study this is, well, for almost every omega, okay, for P almost every omega, then this random measure satisfies. Okay, and the second perspective you can have is the average perspective. And the idea is the following. You want to look at another probability, which I will call P bar x. Okay, and basically, you want to define this probability as follows. So here A is in z to the power z plus and measurable. Okay, and by measurable, I mean measurable with respect to the sigma algebra generated by cylinder events. And this thing is going to be equal to, well, the integral of px omega xn and larger than 1 in A. P d omega. Okay, or if you prefer, the expectation with respect to the environment of px omega okay, so maybe some comment on this. So basically, you're looking at the name says it all. Basically, you're looking at this random measure and you average with respect to omega. So perhaps what you would like to check is that this really defines the probability. Okay, And in fact, the only thing you have to check here, I mean, like the axioms of being a probability are easy to check. What you have to check really is that this thing here is measurable, because we have made a. So just let me make a quick comment about that. Is well defined. So why is it well defined? Because if A is equal to well, x0 equal x0, xn equal xn. Okay, so there is my notation, I guess, is not 100% coherent here, but so if A is an event of this type, then P x omega xn in A is a polynomial in omega x in Z. X in Z, yeah. So in particular, it's integrable. Okay, so you know that this thing is well defined for this kind of events, and then you do the usual monotone class business to show that it's true for every measurable event. Okay, and define a probability. Okay, so what are the advantages of each point of view? I mean, basically, like proving that something holds almost surely for P almost every omega is the same as saying that something holds almost surely for the average measure. So these notions, okay, for some questions, answers might be different for depending on the point of view you're considering, but in other instances they will be the same. Okay, but there is an advantage for each point of view. So in A, you have a Markov process. And yeah, this property of being independent of your past, given where you are, is really useful. Okay, we are going to use it all the time. B is not a Markov process, so this is not good. But it is translation invariant. Okay, so this is something you can check. Is that the distribution of xn under Px is the same as that of xn plus x under P0. okay, well, one way to check that is, well, you apply this formula for these elementary events I've given you. And well, basically, you get the same polynomials here for both things, except that the indexes are shifted. But because this probability is translation invariant, okay, and this can be also quite useful. Okay, and yeah, in the literature, sometimes this thing is called the yield measure. Somehow, for a general statistical mechanics point of view, I think it does not really correspond to what physicists call an yield model. So I prefer the notion of average. But yes.
We're gonna see the case where the omegas are not identically distributed, where this would fail.
Okay, this is not really the focus of this course, except that kind of, yeah. Okay, today and on and next Tuesday I will present a result which is actually true. I mean, you get a result that gives you something about every omega, every sequence of omega. So it's not something that's going to be true. Like almost surely with respect to P, it's something that is going to be true for any sequence in Z. Okay, so in that case, it's not IID because it's any deterministic environment. So it's kind of the strongest thing you can the strongest kind of result you can get. Okay. So okay, so let us ask the first questions that one may ask about this process. Okay. So first question. Is Xn recurrent or transient? So you can ask the question under Px or Px omega. Okay, and just when I write P bar, okay, I mean, of course, there is no dependency in omega because you're averaging over omega. But of course, this thing, I mean, it's not written, but it depends implicitly on P. Right? So it depends on the distribution of omega. Okay, so so what do I mean by that is do we return infinitely okay do we visit infinitely many times all sites in Z, or do we have well, either the limit when n goes to infinity of xn plus infinity, or the limit when n goes to infinity, xn equal minus infinity. Okay, yeah, basically, I mean, I will go back to that in a moment, but you have only 3 possibilities for the behavior. Okay? Because if you're recurrent, you are going to visit infinitely many times all sites. And if you're transient, well, it means that you're going to visit all sites finitely many times. So therefore, it will mean that xn will, in absolute value, converge to infinity. And because your walk is nearest neighbor, basically, well, if you converge in absolute value to infinity, one of those things has to happen. Okay, so let's start. With a simple case for which we know the answer. Then we will try to guess naively what could be the answer for the random walk in the random environment. And then I will tell you what the real answer is, and it's not what you get from the naive guess. So, okay, so simple case. Probability that omega 0 is equal to p is equal to 1 for some fixed p in 0. Okay, so you have a random environment which is not random. So if p is equal to 1/2, okay, what you have is a one-dimensional simple random walk. So Pauli's theorem implies that x is recurrent. Okay, under px omega or p bar, px bar, because these are the same thing. Okay. If p is strictly larger than 1/2, then the law of large number implies that the limit when n goes to infinity of xn is equal to infinity. Okay, and if p is smaller than 1/2, then the law of large number implies that the limit when n goes to infinity of xn is equal to minus infinity. Okay, so yeah, when you have a random environment, you may expect that, well, you might still have a law of large number. Okay, so perhaps you might even have a law of large number in the same sense of what you have for IID random variables. So one we can look at is, well, let's try to compute the expectation of x1. Okay, and well, decide depending on whether it's positive or negative, whether we should have well, convergence to plus infinity, minus infinity, or recurrence. So well, this thing, by definition, it's the expectation of x1. And the expectation of x1, well, it's 1 times the probability that x1 is equal to 1 plus 1 minus plus minus 1 times the probability that x1 is equal to -1. So this is 2 omega 1 minus 1. And you get that the x1 is equal to 2 expectation of omega 1 minus 1. Okay, so a naive guess. Would be that, well, if we have recurrence in that case, and when the expectation is not equal to 1/2, xn goes to plus or minus infinity. Well, this guess is wrong, and it's not too difficult to try to understand why. Basically, what you can do as an exercise is to try to compute the expectation of x2. And you will see that the expectation of x2 is not twice this, because in the expectation of x2, what you will obtain already is expectation of w omega 1 square. Okay, so you have this kind of reinforcement, and then you get that the expectation of this, it does not depend only on the expectation of omega, but on all moments, so it's something. Okay. So we are going to find the right criterion for recurrence and transience. So this is basically the beginning of the work on random one in random environment, and this is due to Solomon in the 70s. And I think, this is part of his PhD, and I don't know if he continued probability afterwards. But so even if you decide to do something afterwards, you might have a legacy that lasts 50 years. Okay, so before giving you what the criterion is, and I'm going to tell you basically, given a sequence omega, how you say whether you're transient or recurrent. Before doing this, I would like to go back a bit to this recurrent transient alternative, because there are something we proved for Polier theorems where we really used translation invariance. So I want you to be convinced that all of this really works. And basically, this will also be an occasion to go back to basically these results you get with path decomposition, but without doing the path decomposition. I will just say, you've done it once, you know how to do it. Okay, so let me write it as a theorem. And the recurrent transient alternative. Okay, so either, because the theorem is, okay, I could write one of the two things has to hold. So either for every x in Z, Px omega almost surely xn visits all Z in ZD infinitely many times. Or for every x in Z, P x omega almost surely for all Z in ZD, the number of n such that xn equals Z is finite. Okay, well, of course, this implies limit when n goes to infinity of so what we have is that P x omega xn tends to infinity union xn tends to minus infinity equal 1. Okay, so either you visit all the sites infinitely many times, or you will drift to plus infinity or minus infinity. And this is true for every omega, not for almost every omega. Okay? Here there is no, I mean, like, it's something about random walk in an environment, not random walk in a random environment.
And there is something similar to this for our dimensional case.
Yeah. The only thing which is one-dimensional is this part. Okay, but all the rest, and these times it will become clear. There is something where we use, okay, it's not true for every Markov chain. Okay. Somehow, if you want, here what we are using is really this kind of uniform. I mean, we are using the fact that for every site you can go to some other site in finitely many steps. Okay, there will always exist a path. You can go and go back. If not, and then there is a general theorem like that, but it's bizarre things can happen, but okay. This is not these are kind of pathological behaviors. This is the normal behavior. Okay. So let me. Okay, this is not the end of the theorem. Sorry. What I want to add is to say, okay, let's define tau x as the infimum of n larger than 0 such that xn is equal to x. So tau n is the first visit time at x. And somehow I want also to study the first return time at x. Okay, and what I want to say here is that A holds if and only if the probability starting from 0 of T star 0 is finite. Okay, so the probability that you that you return to 0 starting from 0 is equal to 1. Okay, so proving this will be really something like the proof of Polya theorem. So for this reason, I will do it with a bit less details, but I will insist on the fact that we have okay. Okay, last time we used translation invariance. We cannot do it this time, so I want to make it clear that this is not a problem. Okay, so in order to prove this, we are going to use a lemma. And we are going to, the lemma is the following. So if P omega x tau star x is equal to 1, then the three following things hold. So first thing is for all y in Z, P omega x tau y finite is equal to 1. So starting from x, the probability that you visit y is equal to 1. Second thing, the probability that starting from y, you visit x, this is equal to 1. And third thing, the probability that starting from y, you return to y, this is equal to 1. Okay. So let me show why this lemma is enough to prove the theorem, and then we will prove the lemma. Okay. Any questions so far? Okay, so ny, okay, is the number of visits to y. Okay, the number of n's such that xn is equal to y. So what we have is that the probability yeah, so this is going to happen eventually, but okay. I'm going to mix things up, but yeah, you can correct in your notes. So okay. The probability that you visit y at least k times, well, this is equal to the probability that you visit y once, okay, and then the probability that you visit y at least k times. Okay, I want this to be true when y is not equal to x, but I think here it's even true when y is equal to x, because in that case, this is equal to 1, so you have no problem. Okay, and this is true just by this concatenation path argument. This works just as before. Okay, so, and again, this thing is also equal to px omega to y. P y omega to star y to the k minus 1. Okay, so this is what we are going to use. So can I erase this? So if P 0 omega T star 0 finite is equal to 1, okay, then Px omega ny larger than k is equal to 1. Okay, why? Well, okay, this being true for 0, basically, is going to imply that this is equal to 1. Okay, it's also going to imply, and now you can use this over there and get the result for x. Okay, so you will also get that this is equal to 1. Okay, or if you want, okay, then what you get first, okay, if you want, is px omega t star t x finite is equal to 1 for all x in TD. Okay, just using this part of the lemma, and then using this again, you get two if P0 omega to star 0 finite is smaller than 1, then the contraposition of C gives that P y omega T y star is smaller than 1. Okay? Because if this was equal to 1, then this would imply, I mean, I can use it there, and this could imply the same thing for 0. Okay, and thus, the expectation of from x omega of ny, well, this thing is finite. Okay, just because this thing decays geometrically. Okay, so I mean, basically, yeah, the proof of Polya theorem is not the same because, in particular, like the number of times you return to yourself, I mean, it's still a geometric everywhere, but it's a geometric with a different parameter everywhere. Okay, but this doesn't really matter. Okay, and like the probability that you return, that you visit y k times, it's also a geometric sequence, but it's not initiated from 1. Okay, so how does this work? The proof of ABC. So somehow I forgot to write it on my notes. So I think it's not. So let's prove the lemma. Okay, let's go. Yes. So I put in normally in the right order. So I want to show first that starting from x, the probability you visit y is equal to 1. Okay, perhaps let's do B first. Okay, so let me call Vy this function here. Vy is the probability starting from y that tau x is finite. Okay, what we know is that V of x is equal to 1. Okay? And the other thing we can say is, okay, Vy is equal to, well, the probability that x1 is equal to y plus 1 times the probability y tx finite knowing x1 is equal to y plus 1 plus the probability that, starting from y, that x1 is equal to y minus 1 times the probability that tau x is finite knowing x1 is equal to y minus 1. Okay, and this is true like if y is not equal to x, of course. Okay, this is always true, but the next step is going to be true only if y is not equal to x. So now, well, this thing here is omega y. This thing here is 1 minus omega y. Okay, and the question is about these other terms. And this is where we are going to use the fact that we have a Markov chain. So, well, if you look at your process after the first step, and if you know where the first step is, basically, what your process will look like is like a Markov chain started from y plus 1. The only difference is that the time index will be shifted by 1, but this is not something which is relevant for these kind of events. Okay, so overall, what you get is that Vy is equal to omega y v y plus 1 plus 1 minus omega y v y minus 1. Okay. Oh, yes. Okay. I put a star here. This doesn't affect the definition. It just affects the definition for y equal x, and then this is true for every y. Okay, and now we're done. Okay, y, Vx is equal to 1. So this thing implies that Vx plus 1 and Vx minus 1 are equal to 1. Okay, because Vx, it's a linear combination of two probabilities, and it's equal to 1. So these two probabilities have to be equal to 1. Okay, and then you expand to all neighbor by neighbor, and you get that this function is equal to 1 everywhere. Okay, so this is, B is done. Now let's try A. So I want to show that, yeah. So A, we've done it already. So this is good. A, it's really the same argument as for the simple random walk. So what do we have? So for A, we have that, well, okay, let's call to x k the kth return to x. Okay, and we have that px omega, the probability that tau y is larger than tau xk. Well, this thing is equal to the probability that tau y is larger than tau x star to the power k. Okay, and this is just the concatenation of path argument. Like, in order for this to be true, you need to basically avoid y for k loops. Okay, so if p x omega tau x star, if this is finite, if this is equal to 1, sorry, then tau xk is finite for every k. Okay, so we get that, well, px omega that tau y is equal to infinity. Well, this is smaller than px omega tau x star tau y larger than tau x k, okay, which is smaller than px omega tau x star tau y larger than tau x star. to the power k, and therefore, okay, this thing is strictly smaller than 1. Okay, just because there is a possibility, okay, to reach y directly from x, avoiding x. Okay, I mean, just take a path of, if you're in ZD, for instance, you could take a path of minimal length and go there directly. And it has positive probability. So, so therefore, because this is valid for arbitrary k, this thing is equal to 0, which is what we want. Okay, and then it remains to prove C. Okay, how does C work? Well, you know that if you start from y, you're sure to reach x. And then if you start from x, you're sure to reach y. So the probability that starting from y to y star is finite. Well, this event, it's included in the following event. So x visits first, well, x visits x and then returns to y. Okay, and when I describe this event, I'm not saying that it doesn't visit y before reaching x, okay? Okay, and well, this thing here is equal to py omega tau star, well, tau x finite p x omega tau y finite. Okay, and this is just by the concatenation path argument. Okay, you'll just describe all the way you can do this, and then once you do this, you can factorize this. Okay, and I think now we have like basically the part of the classification theorem for Markov chains that is useful to us. Okay, ignoring the pathological cases. So, and yeah, this is general. Okay, this is true for every Markov chain. Okay, what we have really used is this important thing right here. That starting from x, it's possible to reach y. Okay, so any questions so far? So now I'm ready to state the big theorem. We are going to prove it next time. First, we are going to see what the theorem implies for the case of random environment. Okay, so basically the theorem I'm going to state. Well, it tells you if I give you the sequence omega, it will tell you whether the walk is recurrent or transient, and also whether it goes to plus infinity or minus infinity, or possibly both. Okay, because in the theorem I erased, okay, the only information we had is that you know the probability is that it goes to one of the two is equal to 1, but you don't have a 0-1 law for this kind of events a priori. so given omega x, we set rho x to be equal to 1 minus omega x over omega x. Okay, and here is the theorem. So, first thing is, okay, I'm going to introduce a quantity which I will call z plus. Okay, z plus of omega if you want. And it's a sum from n equals 0 to infinity of the product from x equal 1 to n of rho x. So, yeah, okay. Yeah, no, okay. No, I will just define this, and then I will state my theorem. Z minus is just, well, the same as Z plus, but basically it's kind of the symmetric version. So, I put a minus here. Okay? And the theorem is as follows. So if z plus is equal to infinity and z minus is equal to infinity, then the random walk in environment omega is recurrent. Okay. But the second part just tells you that this is in fact this is not only a necessary condition, it's a sufficient condition. So if either z plus is finite or z minus is finite, then the random walk in environment omega for every x in Z, px omega xn. Okay. To let me check. Yes. Xn to plus infinity, positive. Okay, and similarly, the Z minus finite is equivalent to for all x in Z, P omega x xn to minus infinity is positive. Okay, so basically you have four. You have xn goes to minus infinity, p omega x almost surely for every starting point x. Z plus, sorry?
C plus.
No,
Oh,
no. Yeah, I should put just infinity here, but. And if z plus is finite and z minus is infinite, then xn goes to plus infinity. P omega x almost surely. And if both are finite, okay, then well, you have this, okay? But the sign of the limit is non-degenerate. Okay. Both plus minus infinity have positive probability. Okay, and because this is a complete picture. You give me a sequence. I will just compute these two quantities, and I will tell you if your random walk is recurrent or transient. Yes, and okay, in this last case, I mean, this last case is a bit pathologic, but basically, yeah, you can say something more here. Basically, the closer you take x to plus infinity, the largest the probability to go into plus infinity is going to be. Okay, so these probabilities are non-degenerate, okay, but they tend to 1 and 0, okay, when x go to infinity in absolute value. Okay, so this is a big theorem to prove. What I'm going to do now is see what this implies for the case of IID omegas. Any question about the result? Okay, I will just erase this last part because the rest is more important, I guess. I will erase this. So for n in Z, I will define un as, okay. No, I will do things for Z plus, and then you will see that for Z minus, basically, things are symmetric. So I will concentrate only on Z plus. Okay, so un, so n is larger than 0, and un is a sum from x equal 1 to n of log rho x. And what you have is that Z plus is equal to, well, the sum from n equals 0 to infinity of exponential un. Okay, so if the expectation of log rho x is negative, okay, then the law of large number, okay, like UN is a sum of IID random variables, and these variables, they are essentially bounded, okay, just because of our uniform ellipticity condition. Okay, I just need them to be L1, so I don't need this full condition, but you see already this becomes useful. So the law of large number tells us that, okay, UN is smaller than, say, expectation log rho x over 2 times n for n notch. And hence, Z plus is finite, almost surely. Okay, so now we have to see what happened in the other case. So you know, I've rewritten the expression of Z plus, so I can just erase it there. If the expectation of log rho x now is negative, is non-negative, then, okay, the lim sup when n goes to infinity of UN is equal to plus infinity. Okay, so when this thing is strictly positive, this is a consequence of the law of large number. Okay, so I'm just going to give you a relatively short proof of this when the expectation is 0. Okay, this is kind of intuitive that this cannot fail to be true. But I think this is kind of instructive to, well, proof statements when they show up, even if they are not surprising. Okay, so, and thus, Z plus is equal to infinity, almost surely. Okay, so basically you have 3 cases. So 1, expectation of log rho x negative. So in that case, okay, this is A, and this is B. In that case, A yields that Z plus is finite, and B plus symmetry yields that Z minus is infinite. Okay, so what we have in that case is that the limit when n goes to infinity of xn is equal to plus infinity. Px omega almost surely. Okay, so the probability that this is true is equal to 1. Okay, for almost every omega, this happens. Second case, well, if E of log rho x equal to 0, B yields that z plus equal infinity and z minus is equal to infinity. Okay, just by symmetry. Okay, so therefore, what you get is that the probability that x is recurrent is equal to 1. Well, okay, is recurrent under px omega is equal to 1. Okay, and of course this does not depend on x. Okay, and the third case, okay, is log rho x strictly positive, and it's exactly the symmetric of the first case. So in this third case, you have the probability that the limit when n goes to infinity of xn is equal to minus infinity px omega almost surely is equal to 1. Okay, so even though with the theorem for arbitrary omega we have 4 possibilities, when you have a random environment you have only 3 possibilities. Either you are transient to the left, or you're transient to the right, or you're recurrent. And okay, the criterion we have is not the one which is a naive one, which is well, expectation of omega x is equal to 1/2. Okay, it's something a bit more involved. But you have this thing that, well, like recurrence is somehow the exception. It's when you really tune the parameter really well so that things are somehow centered. Not centered in the trivial way, but centered in this more twisted manner. Okay, so, yes?
Condition on the expectation of the first one is negative, not less than.
Sorry?
The
So,
condition of the expectation of the log should be negative.
oh, yes. Yes, because this is, yeah. Thank you. Okay, and yeah, so I think this is, okay, this brings kind of a very satisfactory answer to some non-trivial question. Okay, I'm going to prove this in the remaining time. But before that, let me tell you one thing. Now there is a natural question that comes next. Like, when you go to plus infinity, do you go there with positive speed? Do you have a non-trivial law of large number? Okay, so question. Okay. When xn goes to plus infinity, do we have the limit when n goes to infinity of xn over n equals v, and do we have, see, this is kind of a first question, and perhaps more importantly, is this velocity positive? Okay, and yeah, the first naive answer might be, yeah, okay. You start to escape from 0, then you do some independent steps. So things should add up. Well, the problem is that things are independent but conditioned to the environment. So they are independent, but they don't have the same law. So after going away from 0, you might get yourself in some environment that kind of wants to push you back to 0, doesn't succeed, but is good. I mean, it's bad enough so that you get stuck for a long time, and this will prevent you from having positive speed. So this is kind of the next thing we are going to look at. Okay. Okay, I mean, you can also ask this question. I mean, does this converge to 0 when you're recurrent? But I think this is okay. This is much less exciting. Like, this has to converge to 0 when you're recurrent. Like, you have to do really bizarre things for things not to converge. But what you can ask is, do you have a central limit theorem? So when xn is recurrent, okay, what is the order of magnitude of xn? Anybody wants to throw a guess? Oh, yeah, you can try to think about it. You have a guess?
Square root.
So square root of n is a true answer in a very specific case when the environment is not random, which is a particular case of random environment, but it's off by a lot as soon as you consider a truly random environment. Yeah, no, I think it's difficult to guess. There is a heuristic leading you to this, but we are going to come back to this later. Okay. So what do I want to prove? Okay. So this is it. If y, okay, if E of rho x is equal to 0, then lim sup of un, when n goes to infinity, is equal to plus infinity. Okay, what I'm going to prove is something about sum of IID random variables. What I'm going to use, which is not needed, but it makes the proof simpler, I'm going to use the fact that rho x is in L2. Okay. I should put rho 0 here, okay, because all the rho x are. Okay. Okay, and my variables are essentially bounded, so again. Okay, so why is this true? Well, okay, so proof. The first thing is that lim sup of un, when n goes to infinity, is the same as lim sup of un minus uk when n goes to infinity. Okay, for all k in Z. Well, okay, this is no. This is not true at all. So this event and this event are the same. Sorry. Because I'm just subtracting a finite random variable here. Okay, so, well, the good thing is that this thing, it's independent of rho 1, rho k. Okay, just because, well, the terms of this thing after n equal k, well, they only implies rho with larger indices. So therefore, because this is valid for every k, this means that this event here belongs to the tail sigma algebra. It's independent of this for any k, so basically it's independent of everything. So it has probability 0 or 1. Okay, so we just have to show, by 0-1 law, we need to show that lim sup of un is equal to plus infinity. So what I'm going to show is that un is larger than n to the 1/4 infinitely often. Yeah, with positive probability. Well, in fact, yeah, this event, of course, is also satisfies the 0-1 law. So if we show that this also is positive probability, we're done. Okay, so well, the thing is that by central limit theorem, the probability that un is larger than n to the 1/4 tend, when n goes to infinity, to 1/2. Okay, it's a probability that the Gaussian is larger than 0. Okay, here, I mean, basically, we are using a kind of portmanteau theorem. Okay, this is smaller than the probability that this is larger than the probability that this is larger than epsilon square root of n. Okay, so this converges, this other thing converges to the probability that the Gaussian is larger than epsilon. Okay, just because your limiting distribution has no atoms, and then this is true for every epsilon. So. Okay, and the 1/2 is not important. Okay, so now you get this thing that I call Vn to be the sum from k equal 1 to n of indicator uk larger than k to the 1/4. And what we have is that, well, the expectation of Vn well, it's larger than, say, n over 3. Okay, just using this, like I have the sum. Eventually, all terms are larger than 1. Well, eventually, yeah, I have a sum. The terms are converging to 1/2, so the sum has to be larger than n over 3. Okay, so what are we looking at? I will call V bar n to be n minus Vn. Okay, so now let's look at the probability that V infinity is larger than n. Okay, and I want to get a bound on this that does not depend on n, and I will be done. Okay, so perhaps I don't want to do that. Let's do something like n over 6. Okay, but okay, so this thing, it's larger than the probability that Vn is larger than n over 6. Okay, and now it's equal to 1 minus, okay, let's put strictly larger maybe. It's 1 minus the probability that V bar n is larger than 5n over 6. Okay, and now V bar n is positive, so I can use Markov inequality. So this is larger than 1 minus 6 times the expectation of V bar n. Over 5n. Okay, and this is larger, so than 1 minus 6 times 2n over 3 divided by 5. Okay, and okay, this is good. This is larger than 1/5. One minus 4/5. Okay, so this does not really happen by chance. Okay, what I'm saying here is, well, Vn has an expectation which is of order n, but it's also essentially bounded by n. So it has to be of order n with positive probability. Okay, and then the right way to do things is to use Markov inequality, and then you tune the parameters so that things go well. Okay, perhaps not the simplest or the shortest, but relatively simple and short. So I think this is, sometimes it's finding the simplest and shortest is a very long process. So a long and complicated process. So okay, so this is it for today. Do you have any questions? Okay, so yeah, I'll see you on Tuesday, and we will prove the theorem I stated earlier.